Welcome to the first part of our comprehensive series on advanced level organic chemistry. Today, we are diving into the synthesis of organic compounds. To master organic synthesis, you need to understand the chemical properties of different functional groups and know exactly which reagents and conditions to apply. We will be exploring the preparation and reactions of several major groups, starting with alkanes. Let us begin with the preparation of alkanes from alkyl halides, also known as haloalkanes. There are two primary methods here. First, reacting an alkyl halide with a zinc-copper couple in the presence of aqueous ethanol reduces the halide to an alkane. Second, we have the Wurtz reaction. By reacting an alkyl halide with sodium metal in dry ether, we couple two alkyl groups together. This is a fantastic synthetic route when you need to exactly double the length of your carbon chain. What if you need to decrease the length of your carbon chain? You can use decarboxylation. By heating the sodium salt of a carboxylic acid with soda lime, which is a mixture of sodium hydroxide and calcium oxide, the carboxylate group is completely removed and replaced with a hydrogen atom. As you can see in the example, sodium propanoate, which has 3 carbons, is converted into ethane, which has only 2. Another reliable method to prepare alkanes is the catalytic hydrogenation of unsaturated hydrocarbons. Whether you are starting with an alkene containing a double bond or an alkyne with a triple bond, the addition of hydrogen gas will fully saturate the molecule. This process requires a metal catalyst. You can use palladium or platinum at room temperature, or if you are using a nickel catalyst, you will need to heat the system between 150 and 200 degrees Celsius. Alkanes are generally unreactive, but they do undergo substitution reactions under the right conditions. When exposed to ultraviolet light, alkanes react with chlorine or bromine to form haloalkanes. In molecules with different types of hydrogen atoms, like propane, substitution at the secondary carbon is favored, making 2-bromopropane the major product. Alternatively, alkanes can be converted to alkyl chlorides using sulfuryl chloride in the presence of a dibenzoyl peroxide initiator. Let us look at how we apply these reactions in synthesis. If a question asks you to convert methane to ethane, you must increase the carbon chain. First, halogenate methane to chloromethane, then apply the Wurtz reaction using sodium in dry ether to double the chain. Conversely, to convert ethanoic acid to bromomethane, you must decrease the chain length. Convert the acid to its sodium salt, perform decarboxylation with soda lime to get methane, and finally brominate it under UV light. Moving on to alkenes, the primary way to form a carbon-carbon double bond is through elimination reactions. If you start with an alcohol, heating it with concentrated sulfuric acid at 170 to 180 degrees Celsius, or using phosphoric acid, will remove a molecule of water to form an alkene. If you start with an alkyl halide, heating it with a solution of potassium or sodium hydroxide in an alcohol solvent will eliminate a hydrogen halide to yield the alkene. Here is a very specific and useful reaction. If you have an alkyne and you want to reduce it to an alkene without going all the way down to an alkane, you must use a poisoned catalyst. This is known as the Lindlar catalyst, which consists of palladium supported on calcium carbonate and deactivated or poisoned with lead. This deactivation ensures the reduction stops exactly at the alkene stage. The defining chemical property of alkenes is the addition reaction across the double bond. When reacting alkenes with halogens like chlorine or bromine, the solvent matters immensely. If you use an inert solvent like carbon tetrachloride, both halogen atoms add across the bond to form a dihaloalkane. However, if you perform the reaction in water, water acts as a nucleophile, resulting in a halohydrin, where an OH group and a halogen atom are added. This specific addition follows Markovnikov's rule. When adding halogen acids, or HX, to an asymmetrical alkene, the regiochemistry is governed by Markovnikov's rule, meaning the hydrogen adds to the carbon that already has more hydrogens, placing the halogen on the more substituted carbon. But there is a famous exception. If you add hydrogen bromide in the presence of an organic peroxide, the reaction proceeds via a radical mechanism, resulting in anti-Markovnikov addition, placing the bromine on the less substituted carbon. Alkenes can easily be converted into oxygen-containing compounds. By warming an alkene with dilute sulfuric acid, water adds across the double bond to form an alcohol. Similarly, if you replace the water with an alcohol under the same acidic, warm conditions, the alcohol adds across the double bond to form an ether. Both of these hydration-type reactions strictly follow Markovnikov's rule, placing the oxygen atom on the more substituted carbon. Ozonolysis is a powerful analytical and synthetic tool. By reacting an alkene with ozone in carbon tetrachloride at low temperatures, an intermediate called an ozonide is formed. When this ozonide is hydrolyzed using zinc dust and ethanoic acid, the original carbon-carbon double bond is completely cleaved. The result is two separate carbonyl compounds. Depending on the substitution of the original alkene, these products will be either aldehydes or ketones. Oxidation of alkenes using potassium manganate 7 yields different products depending on the temperature. If you use cold alkaline potassium manganate 7, the double bond is partially oxidized to form a vicinal diol, meaning two hydroxyl groups are added to adjacent carbons. However, if you use hot alkaline conditions, the oxidation is much more vigorous. For example, ethene will be fully oxidized, cleaving the bond to form ephene-dioic acid, commonly known as oxalic acid. Under suitable conditions, alkenes can link together to form long chains called polymers. Ethene polymerizes to polyethene using a Ziegler-Natta catalyst, specifically titanium tetrachloride and triethyl aluminum, at 50 degrees Celsius and 5 atmospheres. Propene uses the same catalyst at higher temperature and pressure to form polypropene. Styrene, or phenylethene, polymerizes using a peroxide initiator at 100 degrees Celsius to form polystyrene. Let's trace some multi-step synthesis. To convert propane to propan-2-ol, first brominate propane under UV light, then perform an elimination using alcoholic potassium hydroxide to create propene. Finally, hydrate the propene using acidified water to yield propan-2-ol. For converting butane to ethanol, we again brominate and eliminate to form but-2-ene. Because ethanol has exactly half the carbons of butane, we use ozonolysis to cleave the but-2-ene directly into two molecules of ethanol. Now we transition to alkynes, which contain carbon-carbon triple bonds. The primary laboratory method for synthesizing alkynes is the double dehydrohalogenation of alkyl dihalides. By heating a dihaloalkane with a strong base, like potassium hydroxide, in an alcohol solvent, two equivalents of hydrogen halide are eliminated to form the triple bond. Additionally, the simplest alkyne, ethyne, can be prepared directly by reacting solid calcium dicarbide with water. Alkynes undergo addition reactions similar to alkenes, but they can react with two equivalents of the reagent. Complete hydrogenation with a nickel catalyst yields an alkane, while using the Lindner catalyst stops the reaction at the alkene. When reacting with halogens in carbon tetrachloride, two molecules of halogen add to form a tetrahalide. Alkynes also decolorize bromine water, though the reaction is noticeably slower than it is with alkenes. When alkynes react with an excess of halogen acids, two equivalents add across the triple bond, following Markovnikov's rule, resulting in a geminal dihalide where both halogens are on the same carbon. Hydration of alkynes is particularly important. By reacting an alkyne with water in the presence of sulfuric acid and a mercury 2-sulfate catalyst at 60 degrees Celsius, an enol is formed, which rapidly tautomerizes to a carbonyl compound. Ethyne yields ethanol, while all other alkynes yield ketones. Ethyne has a unique polymerization pathway. Passing it over a heated iron or organonickel catalyst at 60 degrees Celsius trimerizes it into the aromatic ring benzene. Another crucial concept is the acidity of terminal alkynes. The hydrogen attached to the triple bonded carbon is weakly acidic. Reacting it with sodium metal in liquid ammonia forms a sodium alkynide ion. This nucleophile can then react with a primary alkyl halide to form a longer internal alkyne, a vital carbon-carbon bond-forming reaction. Because of their weakly acidic protons, terminal alkynes can be identified using specific chemical tests. If you add ammoniacal silver nitrate to a terminal alkyne, a white precipitate of silver alkynide forms. Alternatively, adding ammoniacal copper 1 chloride yields a distinct red precipitate of copper 1 alkynide. Ethyne, having two terminal protons, will form dicarbide precipitates in both cases. These tests easily distinguish terminal alkynes from internal alkynes and alkenes. Let us shift our focus to aromatic compounds, starting with the synthesis of benzene. We already saw that ethyne can be trimerized into benzene. You can also prepare benzene via decarboxylation by heating sodium benzoate with soda lime. If you have benzene sulfonic acid, heating it with dilute acid between 100 and 150 degrees Celsius will desulfonate it. Finally, phenol can be reduced directly to benzene by heating it vigorously with zinc dust. Industrial and advanced laboratory methods also exist for benzene. Catalytic reforming involves vaporizing cyclohexane or hexane at 500 degrees Celsius over an aluminum oxide or platinum catalyst to dehydrogenate it into benzene. In the lab, benzene diazonium chloride can be reduced to benzene using hypophosphoric acid, also known as phosphinic acid. Additionally, hydrolyzing a Grignard reagent, like phenylmagnesium halide, with dilute acid or simply water will yield benzene. Benzene is highly stable due to its delocalized pi electrons, so it primarily undergoes electrophilic substitution rather than addition. Reacting benzene with chlorine or bromine requires a Lewis acid catalyst like iron 3 halide to form halobenzene. Sulfonation is achieved using fuming sulfuric acid to form benzene sulfonic acid. For nitration, a nitrating mixture of concentrated nitric and sulfuric acids at 55 to 60 degrees Celsius is used to substitute a nitro group onto the ring. To add carbon chains to benzene, we use Friedel-Crafts reactions. Alkylation uses an alkyl halide and an aluminum halide catalyst. However, beware that primary alkyl chains with 3 or more carbons will rearrange to form a more stable secondary or tertiary carbocation before attaching to the ring. To avoid this, use Friedel-Crafts acylation with an acid halide to form a phenyl ketone, which does not rearrange. Finally, under extreme conditions with hydrogen and a nickel catalyst, benzene can be fully hydrogenated to cyclohexane. Methylbenzene, commonly known as toluene, can be synthesized in a few ways. The most direct route from benzene is Friedel-Crafts alkylation, using a methyl halide and an aluminum halide catalyst. Industrially, catalytic reforming of methyl cyclohexane at high temperatures and pressures removes hydrogen to form the aromatic ring. Another classic laboratory method is the Wurtz-Fittig reaction, where bromobenzene and iodomethane are coupled using sodium metal in dry ether. The reactions of methylbenzene depend entirely on your conditions. If you use a halogen with an iron 3 halide catalyst, the methyl group directs the incoming halogen to the ortho and para positions on the aromatic ring. But if you use sunlight or UV light instead of a catalyst, a free radical substitution occurs exclusively on the methyl side chain, forming halomethylbenzene. Like benzene, the ring can also be fully hydrogenated using a nickel catalyst at high temperatures. The methyl side chain is highly susceptible to oxidation. Using a strong oxidizing agent like heated potassium manganate 7 will completely oxidize the methyl group into a carboxylic acid, yielding benzoic acid. If you perform this in alkaline conditions, you must add acid at the end to protonate the benzoate salt. If you only want to oxidize the methyl group to an aldehyde, you must use milder agents like manganese 4 oxide and dilute acid or chromial chloride to form benzaldehyde. Alkyl halides are incredibly versatile synthetic intermediates. The most efficient way to prepare them is from alcohols. Reacting an alcohol with phosphorus pentachloride or refluxing it with a phosphorus trihalide replaces the hydroxyl group with a halogen. An even cleaner method uses thionyl chloride and pyridine, as the byproducts are gases that easily escape the reaction mixture. You can also form geminal dihalides by reacting aldehydes or ketones with phosphorus pentachloride. Alkyl halides undergo nucleophilic substitution. Refluxing a primary or secondary alkyl halide with aqueous sodium hydroxide yields an alcohol. For tertiary halides, simply boiling with water is preferred to prevent alkene formation. Reacting a primary alkyl halide with a sodium alkoxide forms an ether via the Williamson synthesis. Importantly, reacting an alkyl halide with alcoholic potassium cyanide forms a nitrile. This is a critical reaction because it extends your carbon chain by exactly 1 carbon atom. There are a few more key reactions for alkyl halides. Reacting them with silver alkanoates directly yields esters. Heating an alkyl halide with ethanolic ammonia in a sealed tube produces a mixture of primary, secondary, and tertiary amines, which can later be separated by fractional distillation. Finally, reacting any alkyl halide with magnesium metal in dry ether forms an alkyl magnesium halide, universally known as a Grignard reagent, which is a powerful nucleophile for building complex molecules. Finally, let's look at halobenzenes. While direct halogenation of benzene works for chlorine and bromine, you can also use benzene diazonium chloride. Warming it with copper 1 chloride yields chlorobenzene, and warming it with potassium iodide yields iodobenzene. Halobenzenes can form Grignard reagents just like alkyl halides. Because the carbon-halogen bond is very strong in halobenzenes, substituting the halogen requires extreme conditions. For instance, converting chlorobenzene to phenol via the Dow process requires aqueous sodium hydroxide at 350 degrees Celsius and 150 atmospheres of pressure. Picking up where we left off, let's look at the preparation of alcohols. We can synthesize alcohols from alkenes by reacting them with dilute sulfuric acid upon warming, which follows Markovnikov's rule. Alternatively, we can use alkyl halides. Refluxing a primary or secondary alkyl halide with aqueous sodium hydroxide yields the corresponding alcohol via nucleophilic substitution. However, tertiary alkyl halides are prone to elimination reactions with strong bases, forming alkenes instead. To get a tertiary alcohol, we simply boil halide with water. Another reliable method for preparing alcohols is the reduction of carbonyl compounds. We typically use reducing agents like lithium aluminum hydride, which must be dissolved in dry ether to prevent violent reactions with moisture, or the milder sodium boron hydride. In both cases, the reaction is followed by acid hydrolysis to protonate the intermediate alkoxide. Aldehydes are reduced to primary alcohols, while ketones yield secondary alcohols. Carboxylic acids can also be reduced to primary alcohols. Because carboxylic acids are highly oxidized and less reactive toward reduction than aldehydes or ketones, this requires the stronger reducing agent, lithium aluminum hydride, followed by acid hydrolysis. Sodium boron hydride is generally not strong enough for this transformation. Grignard reagents are incredibly versatile for synthesizing alcohols while simultaneously extending the carbon chain. If we react a Grignard reagent with epoxyethane, the ring opens up and we extend the chain by 2 carbon atoms, yielding a primary alcohol after hydrolysis. If we only want to extend the chain by 1 carbon atom, we react the Grignard reagent with methanol, which also produces a primary alcohol. When Grignard reagents react with larger aldehydes, the nucleophilic attack results in a secondary alcohol. Reacting them with ketones yield tertiary alcohols. Notice a crucial detail here. For tertiary alcohols, we perform the hydrolysis step using aqueous ammonium chloride instead of a strong acid. This milder, slightly acidic condition prevents the newly formed tertiary alcohol from undergoing an unwanted dehydration or elimination reaction. Let's apply these principles to a synthesis problem, converting methanol to propanol. We need to add 2 carbons, so epoxyethylene is the perfect choice. First, we convert methanol to chloromethane using phosphorus pentachloride. We then form the Grignard reagent by adding magnesium in dry ether. Reacting this with epoxyethylene followed by acid hydrolysis gives us propan-1-ol. Finally, mild oxidation with acidified potassium dichromate yields our target, propanol. Moving on to the reactions of alcohols. Alcohols react with active metals like sodium to form sodium alkoxides, liberating hydrogen gas in the process. We can also convert alcohols back into alkyl halides. This substitution is typically achieved using phosphorus pentachloride, phosphorus trihalides under reflux, or thionyl chloride in the presence of pyridine to neutralize the hydrogen chloride byproduct. Oxidation is a fundamental reaction for alcohols. Primary alcohols can be partially oxidized to aldehydes using mild agents like hot copper and oxygen, or fully oxidized to carboxylic acids using strong agents like acidified potassium permanganate. Secondary alcohols are oxidized to ketones regardless of the agent used. Tertiary alcohols lacking a hydrogen atom on the hydroxyl-bearing carbon resist oxidation entirely under normal conditions. Alcohols also undergo esterification when warmed with carboxylic acids and an acid catalyst. When reacting alcohols with concentrated sulfuric acid, the temperature dictates the product. At 0 degrees Celsius, we get alkyl hydrogen sulfates. At 140 degrees, ethers form. At higher temperatures, dehydration occurs to form alkenes, with tertiary alcohols requiring the least heat to dehydrate. Now let's examine phenol. Industrially, phenol is produced from cumene, which is oxidized and then cleaved with acid to yield phenol and propanone. In the lab, we can force nucleophilic aromatic substitution on chlorobenzene or benzene sulfonic acid using extreme heat and pressure with sodium hydroxide, followed by acidification. A milder laboratory route involves warming a benzene diazonium salt with water. Phenol is significantly more acidic than aliphatic alcohols, reacting readily with aqueous sodium hydroxide to form sodium phenoxide. This phenoxide ion is a strong nucleophile, allowing us to synthesize esters using acid halides or silver alkanoates, and ethers using alkyl halides. Furthermore, the hydroxyl group strongly activates the benzene ring, so reacting phenol with bromine water instantly yields a white precipitate of 2,4,6-tribromophenol. Shifting to carbonyl compounds, aldehydes can be prepared by the mild oxidation of primary alcohols, heating calcium methanoate, or the catalyzed hydration of ethene. Ketones are similarly prepared by oxidizing secondary alcohols or through the Friedel-Crafts acylation of benzene using an acid halide and an iron catalyst. The carbonyl carbon is highly electrophilic, making it a prime target for nucleophilic addition. Adding hydrogen cyanide produces 2 hydroxynitrils, while sodium hydrogen sulfite yields a white crystalline precipitate. We can also add alkenolide ions to form complex alkenols. For identification, reacting a carbonyl with 2,4-dinitryl phenylhydrazine produces a distinct yellow precipitate, confirming the presence of the carbonyl group. Because aldehydes have a hydrogen atom attached to the carbonyl carbon, they are easily oxidized, unlike ketones. This allows us to distinguish between them using chemical tests. Tollen's reagent, or ammoniacal silver nitrate, oxidizes aldehydes and deposits a beautiful silver mirror on the test tube. Failing solution oxidizes aliphatic aldehydes, producing a brick red or brown precipitate of copper 1 oxide. Finally, let's review the preparation of carboxylic acids. They are readily formed by the strong oxidation of primary alcohols, or aldehydes. We can also hydrolyze alkane nitriles by heating them with dilute acid. A powerful chain-extending method involves reacting a Grignard reagent with carbon dioxide, or dry ice. For aromatic acids, vigorously oxidizing methylbenzene yields benzoic acid. Carboxylic acids exhibit typical acidic behavior, reacting with bases and carbonates to form salts. They undergo esterification with alcohols under acidic conditions. To increase their reactivity, we often convert them into acid chlorides, using phosphorus pentachloride or thionyl chloride. These acid chlorides are highly reactive intermediates, easily converted into esters or amides, which sets us up perfectly for our next topic. Moving right along, let's dive into the preparation of aliphatic amines. First, we can synthesize them from alkyl halides. By heating an alkyl halide with ammonia in ethanol inside a sealed tube, we get a mixture of amines. The ammonia acts as a nucleophile. Interestingly, the primary amine formed can further react with the alkyl halide to produce secondary and eventually tertiary amines. If we want a cleaner single product, we can start with alkane nitriles. By reducing a nitrile using a strong reducing agent like lithium aluminum hydride in dry ether, we cleanly obtain a primary amine. We can easily make that starting nitrile by reacting an alkyl halide with alcoholic potassium cyanide.
We can also prepare amines from carbonyl compounds through reductive amination. A ketone or aldehyde reacts with ammonia in a weakly acidic medium, and a reducing agent like sodium cyanoborohydride converts the intermediate amine into an amine. Amides offer two different pathways. If we simply reduce an amide with lithium aluminum hydride, we get an amide with the exact same number of carbon atoms. But if we use the Hofmann degradation, warming the amide with bromine and sodium hydroxide, we actually lose the carbonyl carbon as carbon dioxide, resulting in an amide with one less carbon atom. Finally, reducing oxenes with lithium aluminum hydride also yields primary amines.
Now, how do these amines react? A classic test is their reaction with nitrous acid. Because nitrous acid is highly unstable, we generate it directly in the reaction flask by mixing sodium nitrite with dilute hydrochloric acid. Primary aliphatic amines react to form alcohols, releasing bubbles of nitrogen gas, a very clear visual cue in the lab. Secondary amines behave differently. They form alkyl nitrosoamines, which separate out as distinct yellow liquids. Tertiary amines simply undergo an acid-base reaction to form soluble alkyl ammonium nitrite salts. Shifting our focus to aromatic amines, let's look at aniline, also known as phenylamine. The most common way to prepare aniline is by reducing nitrobenzene. We typically heat nitrobenzene with a metal like tin or iron in the presence of hydrochloric acid. This reduction initially forms a protonated phenylammonium salt because of the acidic conditions. To liberate the free aniline, we simply treat the salt with a base like sodium hydroxide or sodium carbonate. Alternatively, we can force ammonia to react with chlorobenzene, but because aromatic rings resist nucleophilic substitution, this requires a copper 1 oxide catalyst, high pressure, and a temperature of 200 degrees Celsius. Aniline is highly reactive towards electrophilic aromatic substitution because the amino group strongly activates the benzene ring. For instance, if you add bromine water to aniline, it rapidly brominates at all the ortho and para positions, instantly forming a white precipitate of 2,4,6 tribromoaniline. Another incredibly important reaction is diazotization. When aniline reacts with nitrous acid, again generated from sodium nitrate and HCl, but kept strictly ice-cold between 0 and 5 degrees Celsius, it forms benzene diazonium chloride. This diazonium salt is a crucial stepping stone for synthesizing a vast array of other aromatic compounds. The beauty of the diazonium salt is how easily the nitrogen gas acts as a leaving group, allowing us to substitute almost anything onto the benzene ring. Using Sandmeyer reactions with copper catalysts, we can introduce cyanide, bromide, or chloride. Warming the salt with aqueous potassium iodide gives us iodobenzene. If we want to completely remove the nitrogen and replace it with a hydrogen to get plain benzene, we use phosphonic acid. And simply warming the diazonium salt in acidic water at 50 degrees Celsius yields phenol.
Let's apply this to some specific conversions from question 20. To make benzoic acid from a diazonium salt, we first convert it to benzonitrile using copper cyanide, then hydrolens the nitrile group with hot acidic water. To get cyclohexene, we first reduce the diazonium salt to benzene using phosphonic acid, then fully hydrogenate the ring using a nickel catalyst at 200 degrees. For a more complex target like hexane 1,6-dioic acid, we convert the diazonium salt to phenol, hydrogenate it to cyclohexanol, dehydrate it to cyclohexene, and finally use hot acidic permanganate to oxidatively cleave the double bond, opening the ring into a dicarboxylic acid. Continuing with diazonium conversions, to make benzylamine, we again form benzonitrile, but this time we reduce the nitrile group with lithium aluminum hydride. To synthesize benzamide, we can perform a Friedel-Crafts alkylation on the diazonium salt to get toluene, oxidize the methyl group to a carboxylic acid using permanganate, and then heat it with ammonium carbonate to form the amide. For N-methylaniline, we strip the diazonium group to get benzene, alkylate it to toluene, and then use a modified Hofmann-style amination to attach the nitrogen directly to the ring.
Besides substitution, diazonium salts undergo coupling reactions. Because the diazonium ion is a weak electrophile, it can attack highly activated aromatic rings to form brightly colored azo compounds, which are widely used as dyes. Coupling with naphthalene 2-ol in an alkaline medium produces a brilliant red precipitate. Coupling with phenol, also in base, yields a yellow or orange precipitate. If we couple it with aniline in a slightly acidic medium at 40 degrees, we get a distinct green precipitate. The extended conjugated pi system across the two nitrogen atoms is what gives these molecules their vibrant colors. Let's look at some multi-step syntheses. To convert cyclohexene to cyclohexenanamine, we first add HCl across the double bond, then substitute the chlorine with ammonia under high pressure. To go from benzoic acid to aniline, we convert the acid to an amide using concentrated ammonia, then use the Hofmann degradation with bromine and base to chop off the carbonyl carbon, leaving the amine attached to the ring. To turn benzene into cyclohexenanamine, we first nitrate the benzene, reduce it to aniline, and finally hydrogenate the aromatic ring completely using a nickel catalyst at 200 degrees.
Moving to question 22, let's build molecules starting from ethene. Hydrating ethene with acidic water gives ethanol. Oxidizing ethanol with hot acidic dichromate yields ethanoic acid. If we want ethanoyl chloride, we simply treat that ethanoic acid with phosphorus pentachloride. To make an ester like ethyl ethanoate, we take some of the ethanol we made in step 1, mix it with the ethanoic acid we just synthesized, and warm them together with a few drops of concentrated sulfuric acid as a catalyst for the esterification. To make propanoic acid from ethylene, we need to add a carbon. We do this by reacting ethene with HBr to form bromoethane, then substituting the bromine with cyanide to form propanitrile. Hydrolyzing this nitrile with hot acid gives us the 3-carbon propanoic acid. For ethanamide, we take the ethanoic acid we synthesized earlier and heat it with ammonium carbonate. Finally, to make ethanamine directly, we can convert ethene to ethanol, oxidize it to ethanol, and use reductive amination with ammonia and sodium cyanoborohydride. Now let's tackle question 23, starting from nitrobenzene. The general strategy here is to first reduce nitrobenzene to aniline, then diacetyze it. For phenylethanamine, we convert the diazonium salt to benzonitrile using copper cyanide, then reduce the nitrile with lithium aluminum hydride. For benzoic acid, we take that same benzonitrile intermediate and hydrolyze it with hot acid. If we want cyclohexenamine, we bypass the diazonium step entirely. We just take the aniline and aggressively hydrogenate the aromatic ring using hydrogen gas and a nickel catalyst. To get methylbenzene from nitrobenzene, we reduce to aniline, form the diazonium salt, remove it with phosphonic acid to get plain benzene, and then perform a Friedel-Crafts alkylation with chloromethane. For 1,3,5-tribromobenzene, we take advantage of aniline's high reactivity. We brominate aniline to get 2,4,6-tribromoaniline, then diacetyze the amino group, and finally remove the diazonium group with phosphonic acid, leaving just the 3 bromines on the ring. To make 4-hydroxyazobenzene, we simply couple the benzene diazonium salt with phenol in an alkaline solution. Moving to question 24, starting with propene. To make 2-methylpropan-1-ol, we add HCl to get 2-chloropropane, convert it to a Grignard reagent with magnesium, and react it with methanol to extend the carbon chain and form a primary alcohol. For propan-2-amine, we hydrate propene to propan-2-ol, oxidize it to propanone, and perform reductive amination. To get ethanamine, which has one less carbon, we can aggressively oxidize propene to ethanoic acid, convert that to ethanamide, and use the Hofmann degradation to step down the carbon chain.
To synthesize 2-methylpropanoic acid, we again form the isopropyl Grignard reagent, but this time we react it with carbon dioxide to form the carboxylic acid. For 2-methylpropane-1-amine, we need anti-Markovnikov addition, so we react propene with HBr in the presence of peroxides to get 1-bromopropane. We then swap the bromine for a cyanide group and reduce it. To make a diamine like 2-methylbutane-1,4-diamine, we add bromine across the double bond to get a dibromide, replace both bromines of cyanide groups, and reduce both nitriles with lithium aluminum hydride.
Let's look at conversions from methylbenzene, also known as toluene, from question 25. To make iodobenzene, we first oxidize the methyl group to benzoic acid using hot permanganate, then decarboxylate it with soda lime to get benzene. From there, we nitrate, reduce, diazotize, and finally react with potassium iodide. To make 2-phenylethanol, we use free radical substitution with chlorine and UV light to get chloromethylbenzene. We extend the chain with cyanide, hydrolyze the nitrile to a carboxylic acid, and reduce all the way down to a primary alcohol using lithium aluminum hydride.
Continuing with methylbenzene, to synthesize phenol, we follow the same degradation pathway to benzene, convert it to a diazonium salt, and simply warm it in acidic water. For phenylethanoic acid, we again halogenate the side chain using UV light, substitute with cyanide, and hydrolyze the nitrile with hot acid. If we want phenylmethanamine, also known as benzylamine, we can take that same chloromethylbenzene intermediate and react it directly with concentrated ammonia. Notice how chloromethylbenzene is a highly versatile intermediate for modifying the side chain.
Let's tackle some mixed conversions from question 26. To get methyl benzoate from phenol, we first remove the oxygen by heating with zinc dust to get benzene. We alkylate to methylbenzene, oxidize to benzoic acid, and esterify with methanol. To make 1-phenylpropane from benzene, we perform a Friedel-Crafts acylation with propanoyl chloride, then use the Clemmensen reduction with zinc amalgam and hydrochloric acid to strip away the carbonyl oxygen. For N-methyl and phenylaniline, we degrade methylbenzene down to aniline, then alkylate the nitrogen with chloromethane.
Moving to question 27, to build propanone from methanol, we convert methanol to a Grignard reagent, react it with ethanol to form propan-2-ol, and oxidize it to propanone. To get propane-1,2-diol from ethene, we first need to extend the chain to propene. Once we have propene, a simple reaction with cold dilute alkaline potassium permanganate adds 2 hydroxyl groups across the double bond. To convert chlorobenzene to benzyl chloride, we form a Grignard reagent, react it with carbon dioxide to get benzoic acid, reduce it to benzyl alcohol, and substitute the hydroxyl with chlorine using PCl5. Looking at question 28, to make N-methylethanamine from ethanol, we convert ethanol to chloroethane using PCl5, then heat it with methanamine in a sealed tube to alkylate the nitrogen. To make 2-phenylpropan-2-ol from benzene, we acylate benzene to form acetophenone, then react that ketone with a methyl Grignard reagent to form the tertiary alcohol. For 2-phenylpropan-1-amine, we take 2-phenylethanol, swap the OH for a chlorine, extend the chain by 1 carbon using cyanide, and reduce the resulting nitrile to the primary amine.
Finally, let's look at question 29. To extend 1-phenylethanol to 3-phenylpropan-1-amine, we replace the hydroxyl with chlorine, substitute with cyanide to add a carbon, and reduce. To make cyclohexylmethanamine from methylbenzene, we convert the methyl group to an amine, reduce it to benzylamine, and then fully hydrogenate the aromatic ring using a nickel catalyst at 200 degrees. To synthesize propyne from methanol, we build up to propanone, convert the ketone to a geminal dichloride using PCl5, and perform a double elimination using hot alcoholic potassium hydroxide. We'll continue exploring more complex organic pathways in the next section.
Let's look at the synthesis of propan-1-ol from propanone. We start by reducing the ketone using lithium aluminum hydride in dry ether to form the secondary alcohol, propan-2-ol. Next, we dehydrate this alcohol using concentrated sulfuric acid and heat to yield propene. To move the functional group to the terminal carbon, we perform an anti-Markovnikov addition using hydrogen bromide in the presence of peroxides, giving 1-bromopropan. Finally, nucleophilic substitution with hot aqueous sodium hydroxide yields our target, propan-1-ol.
Moving on to the next synthesis, we are converting cyclohexanol into cyclohexanol carboxylic acid. This is a classic Grignard synthesis. First, we convert the alcohol to a chloride using phosphorus pentachloride. Then we react the chlorocyclohexane with magnesium turnings in dry ether to form the Grignard reagent, cyclohexyl magnesium chloride.
Now we transition into the trial questions section, starting with the UNEB 2019 past paper. These questions test your ability to synthesize various aromatic derivatives. For example, you are asked to synthesize 1-phenylethene-1-amine and phenylethene starting from benzene. Notice how many of these require adding a 2-carbon side chain to the benzene ring, which typically involves Friedel-Crafts alkylation or acylation, followed by further functional group transformations.
The UENB 2018 questions shift focus slightly. You will need to know how to remove a chlorine atom from a benzene ring, how to form an internal alkyne like but-2-ene from a secondary alcohol, and how to convert a primary alcohol, propan-1-ol, into a ketone, propanone. There is also a classic electrophilic aromatic substitution problem, synthesizing 4-amino-benzene sulfonic acid from benzene, which requires careful consideration of directing groups and the order of nitration and sulfonation.
Looking at the 2016 paper, we see a mix of aliphatic and aromatic challenges. You are tasked with synthesizing 4-bromoaniline, which involves nitration, reduction, and bromination. You also need to convert but-2-ene into butanone, requiring hydration and oxidation. Another interesting conversion is from propene to propyne, which tests your knowledge of halogenation, followed by double dehydrohalogenation using a strong base. The 2014 and 2012 exams introduced some unique functional groups. In 2014, you must synthesize a semicarbazone from an alcohol and build an internal alkyne starting all the way back from calcium carbide. The 2012 questions ask for the synthesis of an ester, ethyl ethanoate, from ethene, and the conversion of a secondary chloride to a primary amine, which requires an elimination to an alkene, followed by anti-Markovnikov addition before introducing the amine group. Moving back to 2008 and 2007, notice the recurring themes. Propyne synthesis appears again, this time starting from ethene or propan-2-ol. You also see the synthesis of derivatives like N-methylbenzamide from benzoic acid and propanol phenylhydrazone from ethanol. These highlight the importance of knowing your nucleophilic addition-elimination reactions for carbonyl compounds. In the 2006 and 2004 papers, esterification is a major focus, such as forming methylpropanoate from propene or methylethanoate from ethene. You are also asked to synthesize diethyl ether from ethene, which involves hydration followed by a dehydration reaction at a lower temperature. The 2004 paper also features the synthesis of an azo-di, 4-nitroazobenzene, testing your grasp of diacetation and coupling reactions. For 2002 and 2001, chain lengthening and shortening are heavily tested. For instance, converting propane-2-ol to butanoic acid requires adding a carbon, likely via a Grignard reagent or a nitrile intermediate. Conversely, converting 1-bromobutane to propane requires stepping down the carbon chain. The 2001 paper also asks for the Wurtz reaction to form hexane from 1-bromopropane. The 2000 and 1998 questions require precise control over reaction conditions. In 2000, converting benzyl alcohol back to benzene is a challenging degradation pathway. You also see the synthesis of specific phenol derivatives, requiring diazonium salt chemistry. In 1998, notice the conversion of propanoic acid to ethylamine. This is a classic Hofmann degradation of an amide, which removes one carbon atom from the chain. Continuing with the second 1998 paper and 1997, we see more azo-di synthesis with 4-dimethylaminoazobenzene. The Hofmann degradation appears again explicitly. In 1997, the synthesis of internal alkynes is tested, converting 2-bromobutane to but-2-ine. You also need to synthesize acetamide from ethene, which involves hydration to ethanol, oxidation to ethanoic acid, conversion to the acyl chloride, and finally reaction with ammonia. Finally, we look at the 1987 paper. These questions ask for the synthesis of 1-bromo-2-phenylethane and 2-phenylpropan-2-ol from benzene, testing your ability to perform Friedel-Crafts reactions followed by side chain manipulations. The conversion of 1-iodobutane to propane is another chain shortening exercise, while converting ethanol to ethylamine requires reductive amination or conversion to an oxime followed by reduction. To wrap up this extensive review of organic synthesis, remember that success requires mastering functional group interconversions. You must be comfortable lengthening carbon chains using Grignard reagents or nitriles and shortening them via Hofmann degradation. For aromatic systems, always pay attention to the directing effects of substituents to ensure you add groups in the correct order. Keep practicing these pathways using retrosynthetic analysis, and you will be well prepared for any synthesis question.